so there is, when we have a magnetic field, the magnetic field produces a force, right? Just like the electric field produces a force. It produces it, so it causes charges to move. It causes, it'll even cause wires to move. So we'll see some examples of that. So I want to show you. I'll show you. The first time I want to show you is actually how we can see these forces in action. Okay, so here, so here's this big giant power supply. Has a lot of current. That's the one I use for creating 16 amps. And if you look in the middle here, there's this funky looking magnet that's sort of like a cylinder. And it just produces a really strong electric field. And then the wires are connected to these bars, okay? And then there's like another little light metal rod sitting on top. And what Aiden's gonna do here is he's got this funky setup here where he could swap the direction of the current flow, okay? Where it can be going through one, going from maybe from this side to this side or from this side to this side. Pay attention to what happens to that little rod that's on the top there while he does that. Okay, so in the presence of the magnetic field, right, he's essentially creating a secondary magnetic field by running the current through the wires in those rods. Okay, and we could actually see the force changing directions, going in opposite directions. I thought that was a lot cooler than the magnets flopping around, but whoop. How does that do that? All right. So here's sort of like what is happening, okay? The magnetic field, just like the electric field, exerts a force, okay, on charges, on current, whatever. And so some interesting things we can see here is that if a charge is not moving, if it's at rest, okay, like we see in the first figure, nothing's happening, right? There's no magnetic field if it's not moving. Okay, so there can't be any force. If it's moving in the same direction as the magnetic field, then there is no force. Okay, so the charge or the current has to move in some direction that's not parallel. Okay, there has to be some portion of it that's perpendicular, right? And we could see this with the right-hand rule. So in this image here, if we have the charge moving perfectly perpendicular to the magnetic field, we get the most amount of force, right? And you could see that what do you call it? That right-hand rule here, right? If we do V cross B, then the force will point perpendicular to it, right? If we have, maybe it's not perfectly perpendicular, but maybe there's, a component of it's perpendicular, we'll still get a force, but it just won't be as strong. Okay, so the force that is acting on charges in a magnetic field, right? We did something similar in the previous lesson, right, where we said that the magnetic field was the charge times the velocity, and you curled your hands in the direction of the r hat vector, right, in the direction of where you're evaluating the field, right? Similar thing happens here, okay? But we cross QV into the magnetic field. Okay, and so a couple ways to do this, and I think I mentioned this previously too. The couple ways that you can use the right hand rule. So this picture is kind of a generic cross product of how the right hand rule works. But one way you could do it is you could point your fingers in the direction of the charge's speed, right? So maybe V, right, would be pointing in the direction of the fingers, and you turn your fingers in the direction of the magnetic field, right? So that would be B, right? Or Q, you could say this is QV if you want. So this is sort of QV cross B. Okay, and then when you do this, your thumb points in the direction of the force. Okay, and then like I said, when we started learning about the cross product, is that sometimes this doesn't quite make sense depending on the scenario you're looking at. So another way you could do it is you could, and I'll do the secondary way in green. You could point your thumb in the direction of the velocity, okay, of the charge's motion. Point your fingers in the direction of B, and then your fingers curl in the direction of the force. Okay, so it's not just a one-way thing. It's not just you have to do it this way. There's multiple ways you could do it, right? It's just the fact is that the force is always perpendicular to the plane of the charge and the magnetic field. Okay, so that's a little tricky, but let me let's try an example of that to try to make some sense out of that. So so here we have an electron moving through a magnetic field with a certain speed. And we have two scenarios, okay? And we can figure out what's the force on the electron. Okay, so the first one, part A, is pretty simple. Okay, the magnetic field is pointing perfectly along the x-axis. The velocity of the electron is perfectly along the z-axis. So can you guess which axis the force is going to be along? All right, so remember that the force
out.
So out. That's one way to look at it. So on the screen here we have B is on the x-axis, V is on the z-axis. So which axis, X, Y, or Z, will the force be along?
B.
Along what?
B.
Along B. Okay. So remember, QV cross B, right? So if we cross V, right? V cross B, okay, then Okay, then the force is perpendicular to the plane of V cross B, right? So the plane of V cross B is the ZX axis.
Oh, what the heck?
So the
Oh,
force is going to have to be along the Y axis.
oh, okay. I was staring at B.
Yeah. So probably what Leia said probably makes the most sense, probably coming into or out of the screen.
And then the next one would be B, right?
And yeah, so the next one, um,
Because the plane is on Z and Y.
um, yeah, so yeah, um, so there's going to be part of it that's so it's not going to be as strong, right? Um, all right, let's do the first part first. So QV cross B. So we know the charge of an electron is 1.6 times 10 to the minus 19th coulombs, moving at a velocity of 1 times 10 to the 7th meters per second. Right, and then the cross product, right, is what? When we do the cross product, it becomes QVB sine of the angle. What's sine of 90 degrees?
1.
1, right? So the magnetic field and the velocity perpendicular to one another, right? That's what we just said initially, was that's when we get the greatest force, is when they are perpendicular. Okay, so really this is just QV times B, right? We don't really even have to put the 90 degrees in there because we know that they're perfectly perpendicular. Okay, we could throw an I hat in there for the I hat direction. Let's see, when I did that, I got 8 times 10 to the minus 13th newtons. And if we're doing this in component form, what's the direction then? Remember that K is the I hat direction, Y is J hat, Z is K hat. Right? They told us the magnetic field was in the I hat direction. Okay, so if the magnetic field is in the I hat and the velocity is in the K hat, and we know that the force has to be perpendicular to those, which hat are we going to use? Right? We said it was along, yes, J hat. Right? It's along the Y direction, so it's along the Y axis. So we would say in component form, this is J hat. Okay. Okay. Now, what do we have? Now we have something that's partially in the Z direction and partially in the Y. The Y or the X? I guess it's the Y.
It's the Y.
Yeah, sometimes it's hard to tell with these 3D diagrams. Okay, so so there's in 3 dimensions we have 3 components, right? The I hat, J hat, K hat. So what can we say is going to happen here then?
It's gonna be in the I hat direction.
I mean the I hat. Well, yeah. So let's look at the components. The components of the force in the x, the y, and the z directions. Right. What do we know about the component of the force? What do we know about force in the x direction? What do we know about force when the motion's in the same direction as the magnetic field?
0.
0, right? So right away we know there's not going to be any I hat component. Okay. So then, how about y? So it's partially in the y, partially in the z. Okay. So for the y, all right, we're going to be QVB. Let's see here. There's a different color here. All right, so if this is the y, the component in the y. Here's a component in the z, right? If we're going to cross these, right, and if we're looking at the y direction, we're going to have to do cosine theta, right? Technically. Right? If we want to know what the y component is, right? This vector v has a y and z component. Right? So if we cross the x component with the y component, right? The y component is technically, right? If we do that right triangle trig, this is the cosine. In this situation, since it's 45 degrees, it doesn't matter because sine of 45 and cosine of 45 are the same, right? Okay, so again, 1.6 times 10 to the minus 19th coulombs, 1 times 10 to the 7th meters per second, 0.5 Teslas in the I hat, times cosine of 45 is what, 0.707, and y is the j hat direction. Okay, so essentially the same as what we got for part A, but just times 0.707, right? So for the y, I got 5.7 times 10 to the minus 13th newtons. In which direction? If we're doing k and y, right, what's perpendicular to the plane of k and y? Oh, bleh, x and y, sorry.
B.
Z, right? So this will go in the k hat direction.
I keep getting it wrong.
Sorry, this is tough stuff. All right. And then in the z direction, right, now it's going to be sine, right? Because now we're looking at the opposite side, right? But it's still going to be the same 0.707, right? So it'll still end up being 5.7 times 10 to the minus 13th newtons. But since now we're crossing the x with the z, now which direction is it going to be in? the force?
In the Y?
Yes. All right. So on Y is the J hat. Ooh. It's kind of tough, but as you practice it, it kind of really helps you think about the right hand rule, right? No?
My mind is just not comprehending anything right now.
Yeah. Yeah, this is tough. So, all right. Well, it is time to quit anyway. So, but yeah, we're always dealing with 3 dimensions. Okay. So if we're crossing the plane, any one plane, then, right? So if we're crossing the XY plane, then the force has to be perpendicular, has to be in the Z plane, right? And it's always Q crossed V. It's always Q comes first, cross B comes second. That's important, right? If you do B cross V, if you do it backwards, it's going to be opposite, right? That's how the cross product works. Okay, so if you curl your hands that way, your thumb will point up, right? The positive Z. If we do B cross Y, we have to turn our hand upside down, and then our thumb points down. So next, I just want to show you a couple of places where we see the application to these magnetic forces. So here, essentially what I took from the book, we see this positively charged particle moving in an electric field, and we can see by the X's that it's pointing into the screen. And so what we see here is we could actually get a particle to travel in a circle, right? So circular motion, like we learned about in Physics 151. We're not gonna make you remember all those details about circular motion and apply that, but just want to point this out because it's very important. One of the applications is for particle detectors, and so what I'll do is I want to show you an example of how this works and where we can also apply, try applying and practicing the right hand rule a little bit more. And so it might actually be kind of good that that this lesson's being pre-recorded for you because I have a lot of videos and going back and forth. It's going to be a little irritating, so I can cut all that out when I edit the video and post it. Okay, so what we see here is you see this blue kind of beam, okay, and that's the electron. So this is an electron gun here, shooting out these electrons, and this big, if you can kind of tell, it's a big glass tube, okay, and this is called a cathode ray tube, and basically it's vacuum sealed. I guess not perfectly a vacuum because there's some particles. There's a gas particles in there, and that's the way we could see the electron beam, or else it would be naked, invisible to the naked eye. And then what else we see here? These white circles that you see. These are inside them are coils. All right, there are a whole bunch of turns in those coils. Okay, and there's 2 of them. And we're not going to go into that that too much in this course, but basically when we have 2 coils that are separated and parallel to one other, and the separation distance, you can see the cat's okay, all right? So this, if they're separated by a distance that's equal to the radius of the coil, then we get a special effect where we kind of get a nice, yeah, he's fine, uniform magnetic field here, okay? And so, and it kind of creates a nice uniform field that's going right through the center of this bulb, this cathode ray tube, Okay, and so what I do here in the video is I send the current, okay, through the coils. First, I'm going to do it clockwise. All right, so it's going to move clockwise, and so what that's going to do is it's going to create a magnetic field that's pointing toward the back of this apparatus here. Okay, so kind of behind everything. It's pointing sort of, I guess, into the screen, you might say. Okay, and then when I increase the current, all right, what you'll see here is now the force that's being applied. Right, if we do the right-hand rule, okay, it's initially there. Let's see if I can grab that and pause it. We could see that if you curl your fingers, right? So if I point my fingers in the direction of that electron beam, okay, then my thumb is going to point toward the back of this apparatus, and my fingers will curl upward in the direction that the beam is bending. And if you give it just enough current, just the right amount of current, then we get this circular motion happening here with the electron beam. And you could, depending on how much current you give it, it could be a big beam or a big circle or a small circle. And now I'm going to change it to clockwise so that now the current is flowing counterclockwise through these coils. And so now the electric field is going to point, right, instead of toward the back of the machine, it's going to point out of the screen and toward us. And so you should be able to predict that your fingers will bend downward. Okay, and so now when I turn the current on, we could see, yes, indeed, it does point downward. Okay, and I'll show you here. There's another cathode ray tube that I have here, and basically here you'll see it's a green beam here, but it's essentially pointing. This electron beam is being shot from left to right. Okay, and it's essentially the same sort of thing, except it's a different shaped tube. And that now what I'm going to do is I'm going to bring a magnet, right, an actual bar magnet. Okay, and we see here that I'm placing the south end of the bar magnet near the beam, and so it bends downward. Okay, so again, we could practice the right hand rule where we can point our fingers in the direction of the beam, okay, and the force, we could clearly see it's pointing downward, so the magnetic field has to be pointing into the screen there, okay, and okay, and now what I'll do is I'm going to, right, so now it points, right, so it points downward there, right, and there. Okay. And then when I flip it and I put the north end of the magnet, right, the magnetic field points the other way, and now we're pointing, that magnetic field is pointing out of the screen. Okay, so it's a little bit tricky there to kind of visualize that with the bar magnet. So I think just if we know the magnetic field, and we'll go back to the notes here. But if we know the magnetic field is pointing into or out of the page, then that's the kind of things that we're going to work with. We went over the bar magnet and how it's and how the field lines point from north to south, but it gets a little bit tricky trying to figure that out. But if you can do things like when we say that it's into the page or into the screen or out of the page, out of the screen, that's the extent of what we're going to practice for this course. Okay. And let's see here. So that's one application of when we see a force, a magnetic force being created by a magnetic field. All right, is this circular motion, this bending. We could say of these beams of multiple. So these are like multiple, probably millions of particles we are seeing passing around from these electron guns. Okay, and another cool thing, I've never for sure had the opportunity to see these, the aurora or the northern lights. I think one time last summer I might have, but it was hard. It was really hard to tell. So we're here in Massachusetts anyway. We're pretty far up north. I guess depending on your reference. But as far as if we can think about the United States, we're pretty far north, but it's still kind of a bit too far south of the poles, of the North Pole, to actually see these. Okay, and so what happens is if we look at the Earth, okay, let's see here, and we remember that the Earth is sort of like shaped like this bar. It's equivalent to, it has this magnetic field that's sort of like a bar magnet, right? It's not a bar magnet in there. We think it's molten lava moving around, and we know that if this is the North Pole, right, and this is the South geographic pole, what we remember, what we said was that basically the North geographic pole has a south magnetic pole, and these are all just based on what we've defined as of magnetic north and magnetic south, and geographic north and geographic south. And so the north magnetic pole is toward the south geographic pole. And so we know that a bar magnet, right, is creating these field lines that look like this, right? So that's sort of what the Earth's magnetic field looks like. And it's very important because it blocks out a lot of deadly radiation from the sun. And what happens here that's pretty cool, is that basically when these particles from the sun come, they usually they come and they hit, and basically the magnetic field of the Earth bends them away, so that we're not exposed to all the radiation. But occasionally there are some particles that get caught in the field, and they find their way. They kind of get pulled toward the poles. All right, and so that's why it's difficult, or it's easier to see this effect near the poles, the north and south poles of the Earth, as opposed to somewhere else down further toward the equator. And so that's pretty cool. And the colors, just have to do with, if you recall, things like the atoms being excited, and we get this emission of photons when atoms get excited. So that's kind of going more into quantum mechanics, but that's a part. Some of that you probably, if you recall, you might have done in a chemistry course. So it's sort of the same idea here, that this field is causing a force on charged particles, and we also see when charges. So far we've just been looking at charged particles that are being deflected, or a force is being acted on them by the magnetic field. But this can also happen in a conductor. And that should make sense because the conductor pushes charges through it, and creating a current. Okay, and so when this happens, we call this the Hall effect. And that's not that important to know, unless maybe you're going to do some electrical engineering. and we have there are these sensors called Hall effect sensors, and so you can install them like in an Arduino or something, and you can actually use it to measure a magnetic field. Okay, and I'm not sure if that's the way that your IOLab device, if it's a Hall effect sensor in there or not, I'm not sure, but that's kind of an easy, cheap way to actually measure magnetic fields. So I think that they only really cost maybe a few dollars if you want to do some sort of experiment or measure magnetic fields. Okay, so a current carrying wire, right, is also going to create a magnetic field, and there's also going to be a force from it. But if you recall, right, back here when we said if the magnetic field is in the same direction, or that's at rest. If the magnetic field is in the same direction as the charged particles, then there's no force that's going to happen. So if they're parallel, there's no force. Okay, and so what I have here in the first figure is we have a current flowing from bottom to top, and the magnetic field is also going from bottom to top there, and so they're in the same direction, and so we're not going to see any force if this happens. Okay, but if you have a magnetic field that's parallel, or not parallel, perpendicular, or at least a portion of it perpendicular to the current, then like we have here where we have the magnetic field going into the screen and the current going up, right, then we are going to have a force. Okay, and so we said that the force exerted by a magnetic field on a charge was the charge times the velocity of the charge, and that with the cross product with the magnetic field. Okay, and so that was for charges, right? How we find the force on a charge. So we can come up with a way to find what is the force on a current carrying wire. Okay, and I know when I've recorded videos in the past, pre-recorded videos, I have a tendency to go fast. So I'm going to try to be conscious of that and try to make sure I'm slowing down here. So with the current carrying wire, right? Remember, what is current? Current is related to charge, right? It's how much charge there is over a certain time interval, and we know that time, right? Velocity is distance over time. I'm going to do length L over time, over time interval, because we're going to talk about the length of a particular wire. Okay, and so if we rearrange this and solve for delta t, we see that it's length over velocity, and then if we take that and insert that here, okay, we'll see here. I'll show out all the work here. Then it's going to be QV over L, okay? And QV, right, is what we had the first part of our cross product for determining the force, right, on a charge. And so if we move the L over here, then we have IL, so the current times the length is equal to the charge and the speed of the charge, right? So if those two are equivalent, then we can rewrite our original force equation as IL cross B. Okay, and so that's how we would determine the force on a current carrying wire. Okay, so let me show you a couple more demonstrations here of this. Okay, so so this one's a little tricky to see everything going on here, but here we have this this funky magnet, this in black here. And basically what it does is it's kind of bent here, and the whole thing's not a magnet. There's a magnet here and here, and what it does is it sort of creates one side is north and one side is south, and it creates a nice strong, very strong magnetic field in between them, right? So this is only like maybe an inch and a half or so distance in between. And then this red wire is being hung here. And over here, I got a car battery that we're going to run the wire through. So it's a lot of current. And then we're going to, I'm not sure who's doing this here, the demo here, but we have a switch here that will send the current one way and then another way. Okay, and we'll see the force that's actually going to be applied on the wire. Okay, and you can see that, right? So we see that it goes one way, right? Oops. Grab that there. Right, it's basically flies upward, right? So we see a force going upward, right, when the current's going one way, and then what's wrong with my mouse, right? And then when the force is the other way, it's pushing that wire down. Okay, so again, I'm not gonna give you anything like this for a problem, but it's just kind of to show you that this force is actually real. This force, we can see this force in real life if we have strong enough current going on. Okay, and then I'll show you one more here. I'm talking through all the in between, so I guess I can't really edit these parts out. So, but here now now we have two wires that are parallel to one another. Okay, and again, this is from MIT, but again, there's a big car battery, and we're going to see that. This time, what they're going to do is they're running the current through the wires in opposite directions. Okay, so I don't know if maybe the current's going up in one and down in the other. And what we see is that they repel one another when the currents are in opposite directions. Okay, and then he's going to flip the switch the other way, and now when the circuit's hooked up that way, the way they have it there, it's allowing the current to go through in the same direction. And when they're going through in the same direction, they are attracting one another. Okay, I didn't talk during that part, so I could cut it out. All right, so and so I kind of have I took this from the book too, so maybe it might be useful if you to look at those pictures in the book, or if they're already here, whatever. But you can see here what's happening in this first image, just like we saw in the video demonstration. When the currents are going in the same direction, right? We see that they're attracting one another, and why is that? Well, we could see here when we look at the magnetic fields that are created, right? We have a field on one side, right? It's pointing out of the page. A field on one side is pointing into the page. Those are opposite fields, right? Like north and south. And so they want to attract one another. Whereas when they're going in opposite directions, you could see that right now, both on these sides, they're both going into the page, okay? And so they're going to repel one another. And I guess one thing I should point out to you, and it's in the notes here, and it says here that the field B1 created by current 1 is this, and then B2 created by current 2 is this, right? So we know that. I think this picture can be a little bit confusing. That's why I want to point this out, because right, we know that in a current carrying wire, the electric field of the wire does not look, it's not into the page on both sides, right? We know that if we have a wire, come on, oops, nope. So if we have a wire like this, we know that if the current's going one way, it's going to be into the screen on one side, but out of the screen on the other side, right? Right. Remember that right-hand rule. If the current's going in the direction of your thumb, it's pointing out one way, but then when you complete that circle, right, it's pointing up one way, but when you go around the other way, it's pointing down, right? Or into the screen, out of the screen. And so I don't want that to confuse you here. And that's why they have this note in the book pointing to that. So, and so what we can do here, that can be useful for scenarios where we're dealing with a couple of wires that have current. We can actually calculate what's the force that they're exerting on each other, right? And so they're exerting forces on each other, so they're force pairs. So they'll exert equal and opposite, or equal forces in opposite directions. And so remember that we said force was I, the current, times the length, and the cross product of that with the magnetic field. Okay, and if the current is perpendicular to the magnetic field, like it is here, right? The wire's perfectly in this direction, and the magnetic field is perfectly into the screen. Well, then the cross product just becomes, right? It's ILB, right? It's perfectly perpendicular. It's only when we have a component of it that's partially perpendicular that we actually have to do the cross product and use the sine of that angle. Okay, and so if we look at the force being exerted by one of these wires on the other, okay, and we'll look at what's the force that that's exerted by the lower wire on the upper wire. Okay, we could say that it's the current of, we'll use 1 for that upper wire because they call it I1, times the length of the wire, okay, times the magnetic field caused by, times the magnetic field caused by the second wire. Okay, and we know that the magnetic field from the second wire is mu naught current of the second wire over 2 pi times the diameter. Okay, so that's just another way that we could rearrange this when we're saying that these are equal to one another. Okay, and we know that the current of the first wire, or we could just rearrange this a little bit more here, make it a little bit simpler here. So mu naught, we'll just kind of basically take these and put them in the numerator to make it a little bit cleaner looking. Okay, and so this is basically the relationship we have, okay, between the force between any two wires. Okay. Okay, and so the last thing here, we're not going to do a whole lot with this, but when there is a force, recall there's a torque, right? Torque is the rotational equivalent of force, and so like I said, we're not going to do any kind of problems or calculations with torque from a magnetic field, but I just want to point it out because it's so important. It's the basis for electric motors and for generators, and basically what it does is that when we create a loop, a coil of wire, and put some current through it and put it in a magnetic field, we get some rotation here, and so that's how we take advantage of these kind of things to create electric motors, which we see all kinds of places, and now we have big ones in electric cars. And then the generator is basically the opposite of the electric motor, right? So the electric motor, we're using the magnetic field and electricity to create some mechanical energy, right? So get something moving, right? Whereas a generator is we use some mechanical energy to kind of do the opposite, to store that energy. And so so one last demonstration then I'll show you is actually this force on a loop of wire that has some current running through it. Okay, and so this is kind of a little ancient demonstration here with one of our older power supplies you can see in the back. But basically in the middle here, there's a loop of wire, and it's got like some cardboard that it's wrapped around just to kind of help shape it into a loop. That's all it's really there for. And it's being hung, and it's going to have a lot of current passing through it. I think something like 20 amps. And you can see he did a sloppy job here of putting the magnets on these pedestals, but you can see that the red here is the north pole facing one way, and then we got the south pole facing this way. And it's sort of like that the previous video where we had that magnet that was kind of like a big black U, and then it formed one pole facing the other pole to create that nice strong magnetic field in between. Okay, and so when he turns the current on, right, one way, we see that the loop spins, right? And now he's gonna have the current flow through the opposite direction, and we get it. The coil is going to turn the other way. All right, so so I just want to point that out to you in case you ever have to encounter that in the future, and it's kind of a cool thing to really think about as far as everyday life. Just we encounter electric motors in all kinds of places, and also generators. Okay, and so the final thing here is just want to talk a little bit about where does the magnetic field come from? And I think a couple classes ago, somebody asked about do we know why magnetic fields exist or something. I'm not entirely sure, but I remember after the lesson thinking that maybe I didn't actually, maybe the question that was asked was not what I thought was asked. So, so we do kind of know a little bit about where magnetic fields come from. And so that's what I'll just show you here too. This is not, anything we're gonna really get deep into, but it's just kind of interesting. Why we have this. So if we look at the classical model of the atom, right, where we have an electron orbiting a positively charged nucleus. Basically in that model, right, what do we have here? We have an electron traveling in a loop, right? And that's sort of like a loop of a current loop, right? Where there's a current flowing through a loop of wire, okay? And so if we have a charge that's moving, right, which we know the electron moves in the atom, then we have a magnetic field. And so the electron itself basically behaves like a magnetic dipole. And what we call it the magnetic moment. We say that the electron has a magnetic moment. This is not really too important to know, but it's interesting if you ever get more into chemistry, I guess, and all the quantum mechanics that goes behind it. Moment, right? Or sometimes we call it spin. Okay, and this kind of really gets into particle physics too. So so the term spin is kind of misleading. There's nothing that's actually spinning. I believe that the term spin comes from the original or this old model of the atom where we thought that the electron was spinning around the atom. But magnetic moment is a little bit more precise because we're talking about like torque in the moment arm, and so nothing's really spinning, but there is movement of a charge, so it's creating an electric field, right? And so this is an atom, right? So all atoms have some sort of magnetic moment to them, but in most elements, the magnetic moments of the atoms are just kind of randomly arranged, okay? And so that kind of gives the material a net magnetic moment of 0. Okay, so most materials we know are not magnetic, even though the electrons are moving in them and creating a magnetic field. Okay, but they're just kind of pointed randomly in different directions. And so we don't really see magnetic materials in everything. But in materials like iron, okay, which is very susceptible to magnetism, right? The magnetic moments, they mostly line up in the same direction. And so that's kind of an interesting feature of these kind of materials. We call these ferromagnetic materials. If you ever look up a video on ferrofluid, there's some interesting, fun kind of things you could do with that, because it's basically a fluid that's magnetic, and you can make all kinds of cool, I guess, shapes or whatever with them. It's very messy too. So if you ever buy a kit of that, make sure you wear some junk clothes. And so if we have a typical, like say a piece of iron, there's lots of, what happens is that you get these regions, okay, which we call magnetic domains, okay, and that's what the second picture here is of. And so we see these funky shaped pieces inside of an atom, and these are the magnetic domains. And so what this means is that in each of these domains, the magnetic moments of all the atoms in the domain are are all aligned. They're all lined up and pointing in the same direction. Okay, so so they're still random. You can see but the domains, you got lots of atoms in these domains that are all lined up. Okay, but if we put the iron in an external magnetic field, that field exerts a force and a torque on each of the domains. And then the torque causes the domains to line up, to rotate until they're lined up with that external magnetic field. Okay. And we could do this by bringing a magnet nearby it, right? And that's why if you bring a magnet near a paper clip or something, right, it's going to jump up to it. Okay. Or if we, like we learned about solenoids, if we run a current through a solenoid, we can do that too, right? And we basically call that an electromagnet when we create a solenoid and run power through it. It creates a nice magnetic field, and it can attract other materials to it. And one way to actually do that is to place something ferromagnetic, something maybe iron, and inside of it. So an easy way to do this is just wrap some wire around like a nail or something, several times, and connect it to a battery, and boom, you've basically got an electromagnet, like the big thing we talked about in the junkyard. And so if we actually do this, if we place certain materials in a magnetic field, these ferromagnetic type of materials in a magnetic field for a long period of time, what we see is that the domains, right, can actually kind of stay lined up even after the field's been removed. So I should have picked this video out too. I'm just thinking of it now. But if you have an electromagnet and bring it near a piece of metal, like a light thing, like a paper clip or something, and you turn off, right, it gets attracted because of the current flowing through it, creating the magnetic field. But if you turn off or disconnect the battery from it, you'll actually see that the paper clip will kind of stay hung there, still stay attracted to it for a while because it's maintained some of that those magnetic moments in the domains pointing in the same direction. And this is how we can actually create permanent magnets is by doing this. So that's one way we can create permanent magnets. Okay, so now you should be able to finish the homework 8 here. The rest of the problems, there's one problem that might be useful to look at in the extra example problems on the Moodle page. And so in this lesson, we learned to describe and quantify the magnetic force on moving charges and on wires, current carrying wires. So remember, we came up with one expression for the cross product if we're talking about just an individual charged particle, and another force, basically the same thing, but if we're dealing with a current carrying wire. All right, and then we said if we have a couple of wires, we have two wires that are parallel to one another, well, they exert an equal and opposite force on one another, and this is how we can kind of relate that force. Okay, and always we're dealing with that right hand rule. Okay, so hopefully I didn't talk too fast the whole time. And all right, so that's it for that.